projection of a vector onto another vector. Last time we had discussed dot product of vectors, which we shall now use, to derive a formula for calculating the projection of a vector onto another vector. And of course, this concept of projection of vectors is very important in physics, as it is used on inclined planes. So let us consider the following geometric idea: vector A and vector B inclined at an angle theta. Imagine for a second that there is a sun ray here directly above vector A. Now what we would expect is that this sun ray will cast a shadow of vector A on B. Will cast a shadow of vector A on vector B. So I call the initial point here MO rather, and call this point here the terminal point of this shadow M. Then we are saying here that OM is a shadow of vector A, which is cast by the effect of this sun ray on vector A on vector B. And of course, it is obvious here and very clear that this shadow OM, which we now call the projection of vector A on B, is nothing but what? The scalar multiple of vector B. Meaning that this vector OM could be smaller than vector B or longer than vector B in length. Vector OM is what we refer to as the projection of vector A on vector B, and written as projection of vector A on vector B. It is this vector OM that we wish to know. So we have a rectangle formed at this point at M, so that this triangle here OM, if you like OMP, whatever, becomes a right angle triangle. And so we can apply a SOHCAHTOA here to get some relationships. So this is adjacent to this angle, this is hypotenuse. So we can write out that the cosine of angle theta is nothing but what? Adjacent. What is the adjacent? OM. Adjacent is OM over hypotenuse. What's the hypotenuse? Hypotenuse is OP. OP. Which can be written again as, what is OM? OM is nothing but what? The projection of vector A on vector B. And what is OP? OP is vector A. And what we are interested here is the length of vector A, which is just the length of vector A. So cos theta is equal to this. What we want is a projection of vector A onto B. So I'll make this a formula, the subject of formula. So I have that the projection of vector A onto vector B is equal to what? The length of vector A times what? The cosine of the angle between vector A and the projected vector. However, we recall from our dot product that given two vectors A and B, that in this case here we have our vectors here A and the projected vector A on B, that the dot product of two vectors, let's say A dot B, if you recall, is equal to what? The length of vector A times the length of vector B times the cosine of the angle between vectors A and B. So that we can make the cosine here the subject of formula, and we have that the cosine of the angle theta is equal to the dot product A dot B divided by what? The length of vector A times the length of vector B. So if we go back to equation star here, where we have cos theta, we now replace with the whole of this. What do we now get? We now get the projection of vector A on vector B is equal to the length of vector A times the length of vector B, beg your pardon, the length of vector A, we are here, times, what's the cosine of theta? Cos theta is equal to, let me rub this off, let me take it again, projection of vector A onto vector B is equal to the length of vector A times the cosine theta, which is now what? Which is now the dot product of A and B divided by the length of vector A times the length of vector B. So obviously the length of vector A and the length of vector A here will cancel out, so that we now have that the projection of vector A onto vector B is equal to the dot product of A and B, A dot B divided by the length of vector B, or the length of vector B. So what is this? A dot B is a scalar, and of course the length of B is also a scalar. So this tells us that this formula just gives us the length of the vector OM, which is the projected vector of A onto B. So the projection, on the other hand, of vector B onto vector A will be the dot product still of vector A and B divided by what? The length of vector A, or the length of vector A. So let's take one quick example to wrap up. So example. So I have here two vectors are given, A and B, 2i plus 3j plus 4k for vector A, I plus 2j plus k for vector B. We're asked to find the projection of vector A onto vector B. And we have seen already that the projection of vector A onto vector B is equal to the dot product of vector A and B divided by what? The length of vector B. So we need two things. We need the dot product of vector A and B. We also need the length of vector A and B. So first, dot product. So the dot product of vector A and B is what? What are the components of vector A? We have here 2, 3, and 4 dots. Vector B, 1, 2, and 1. So the dot product would be 2 times 1 is 2, plus 3 times 2 is 6, plus 4 times 1 is 4. So that 4 plus 6 is 10, that is 12. That's the dot product of A and B. What is left is the length of vector B. So the length of vector B is equal to the square root of 1 squared plus 2 squared plus 1 squared. That is equal to the square root of 1 plus 4 plus 1. Square root of what? 6. So we are set. So the projection of vector A onto vector B is equal to A dot B, the dot product of A and B, which is what? 12, divided by the length of vector B, which is what? The square root of 6. Of course, we can go ahead to rationalize this. That becomes 12 root 6 over 6, which is equal to 2 root 6. So that's the length of the projection of vector A onto vector B. You can go ahead to find the projection of vector B onto vector A, in which case the formula now becomes A dot B divided by what? The length of vector A. Thank you, and bye-bye.